This problem is the classic finding the volume of a pyramid that has a square base of side S and height h. So square base, side S, height h, and it is a pyramid. So over here we have the drawing of the pyramid, and then we go up a height, a certain height up here to right around here, and we take a cut there, a slice, and we see it's a rectangular box slice, and it has a little delta y height to it. And the problem is that we don't know the width or the length of that rectangular box. We have to set up a ratio relationship somehow using our S side, which is the same as this S side, as you can see, and draw this green rectangle inside there like this, and then take that and bring it over to here so that we can have it flat so we can see. So it does have a side S right here, and it does have a height down the middle of height h. So we want to know how wide is that cut at a certain height h. I'm sorry, at a height y, a certain y height. So I've drawn the cross section of that slice right here, going like this around here, and it's a delta y slice, and up at a y height, what is the a? How far across is it? So a is to h minus y, as s is to h. So there's your similar triangle relationship. Solving out for a, you algebraically get this. So a volume of a slice, that red slice, is a squared, because it is a square, times the height of that rectangular box, which is delta y. But we substitute in what a is, and we get this expression. So the volume of the pyramid is going to be summing all the slices up as y goes from the bottom up to the top at h. And here's our expression. Now what we do is right there we check it. What I mean is check the extremes. So when y is 0, you should be at the ground floor. So you should have an s squared delta y cut there on the ground floor. So the ground floor is looking like this. It would be down here. That's the kind of slab or slice you should have when you're down on the ground floor. Okay, so if you back over to here, if you have y equals 0, plug in, picture putting 0 in there. You're going to get the h in there, cancel out with the h over here. So these two are going to cancel out, and you're just going to get s squared delta y. And that's exactly what this should be, s squared delta y down there on the ground floor. So that's checking out. And then going to the top, the very extreme top, when y is h, when y gets all the way to the top h, picture what's happening there. So put an h in your mind here on this y. It'll be h minus h is 0, so we'll get 0 delta y, and that's exactly what it is. At the top, you have a point. So it's 0 squared delta y up there for the volume of the slice. So always check you're running from 0 to h. Check to see if the volumes of the slabs are progressing from the bottom ground floor all the way up to the top, and it'll all work out from there. So then we convert that into the integral as the number of slices goes to infinity and delta y goes down to 0. You have this integral. Factor out the constants always. Then I use that algebra trick. Because it's squared, I can change around the h minus y to y minus h, because it's a square, only because of that. And then, because if I did a u substitution, dy or du would equal dy, and I don't have any harm, I can just go ahead and do this antiderivative, y minus h to the third over 3. Normally we would have to do a u substitution, but in this case works out nice. And to believe that, just differentiate this back and you'll get y minus h quantity squared. Evaluate to 0 to h, and it comes out the classic volume of a pyramid, 1/3 s squared h.